Yeah, hello folks, we are coming to the part 6 video of this exercise, what is that, miscellaneous exercise. Now what we are doing here is there are two problems which are to be evaluated and one problem which is to prove that problem. Let's see how much we can do it. Evaluate means we have to find the value. We can look at this determinant. You have x, y, x plus y, y, x plus y, x plus y, x, y. What we could do is do the simplification and then we expand and find out the answer right away also you can do, but then that will be a lot of work. So we will try to use the properties and try to make this determinant as simple as possible, and once the determinant has become simple we'll expand and get the answer. So what is the best thing that we could do? There's no idea. It's like everybody has got one's own way of doing it. Let's go in for a C1 minus C2. Let's check how it will come. Let's consider a C1 minus C2. What will happen? X minus y minus x minus y. So y will cancel, minus x will remain. Minus x. So y will remain. Y, x plus y, x plus y, x, y. See, we have to get maximum number of zeros and ones so that it's very easy for us to solve. That's our idea, and then we can expand after that so that it is easy to expand. That's our idea. Get zeros and get ones. So if we plan to have these two added up, certain things may simplify. We don't know. We'll check. We will have a C3 operated as C3 plus C1. We'll just check. So what will happen? This x minus y minus x and y, it will stay as it is. This y will stay as it is. X plus y will stay as it is. X will stay as it is, and you're adding. So you're adding x minus y. So 2x will remain. Then x minus x, so 0 will happen. Y minus y will 0 will be happening. If you want, you can take the 2x common out from C3 because nothing is left. So if you take the 2x common out, then you're left with x minus y minus xy, y, x plus y, x, 1, 0, 0. That's our idea, to get ones and zeros. Now actually getting two zeros in a matrix is determinants is fair enough. It simplifies your work quite a lot. Getting two zeros itself is quite good, and a 1 there, quite fair enough. If you can stop right away, or if you want you can do one more step like adding these two. If you want you can do that. So if you want you can do C1 plus C2 if you want. Otherwise at this step you can expand. So maybe C1 becoming C1 plus C2 if you want, you can check. So 2x is there already out, and when this gets added up, x will remain, then added up, so y will remain, and added up x plus y, and then you have y, x plus y, x. It doesn't do much good actually. Yeah, it is not doing much good because it's not giving you zeros and ones. Our idea is to get zeros and ones, and this is fair enough. At this step itself you can expand. Okay, so now let's check what will happen. We're going for an expansion. We should know that zeros here, because of the zeros here, the first and the second term will not give you any values. For example, if you take x into, you're going to get 0. You take y into, you'll get 0. So it's only this last one which is going to give you value because of the zeros here. Right, you can sit and expand and see, and you get to know how it is. So basically when you expand the determinant, it is only this entry which is going to give you 1 times xy, right, minus x plus y the whole square. So what is remaining? 2x times xy minus x squared minus y squared minus 2xy. Yeah. So we are left with minus x squared minus y squared minus xy. No, that is not such a... I'll just get back. Well, just a minute, just a moment. I'll just have a small check. Yes. Okay, let me see whether all this is very appreciable or not. Okay, then when it is getting added up, it will become 2x 0. Yes, that is a mistake. Here it is 2y. this is addition, so it is 2y. So you cannot have the 2x coming out. 2 can come out. You are left with a y. Right. In the next step, we have done C1 plus C2. So yes, so there is the problem. I was wondering, there is some error. So let's rectify that. This is a y here, and there is no 2x. It's only 2. Right? There's a y here. Okay. So what happens is we had done. Why should we ever do that C1 plus C2? Because as I said, our intention is to get as many zeros and as many ones as possible. So, and then therefore there is an x already because we couldn't take it out. So this is a scenario, and suppose if I add this up, then you're getting x, you're getting y, and you're getting x plus y. That is not much. That's not anything great. And our idea is to get one more zero somewhere. So whether that is possible. Yeah, I think we can do C1 minus C3. Let's try. C1 becoming C1 minus C3. That mistake, that y. That is why we unnecessarily did that step. That's not required. C1 minus C3. So we are doing minus x, which leaves minus y. Then we are doing, this is 0, so that doesn't leave anything. Then y minus y, that's 0. So already there's a 2 there. And leftover terms y, x plus y, x. So that's what we intended, no? One more 0. Yeah, that's all. Quite okay. Now you could do the minus 2, you could take it out, and we'll expand from this thing. You could do one thing, you could take the minus out. So it is y, x, 0, y, x plus y, x, x, 0, y. And let's expand and see what's coming. So it is like minus 2 overall times y into y times x plus y, then minus y times x squared, then last term x times x squared, x squared. Okay, so it's minus 2 times, let's expand all this, y squared x, y cube, x squared y, plus x cube. Yes. See this entry, minus y times, it is xy, just check, minus y times, it is xy, so it is xy squared. As a result, these two will get cut, and you have minus 2 times x cube plus y cube as the answer, right? But space constraint sometimes creates trouble. You should have a lot of space, so that no problem. Okay, that's about it. Then we are coming to our next problem. That's also an evaluate problem. They have given us a value and they are asking us to find out what is the value of this determinant. This is relatively better. Why? Because we have the ones. At least we know that we have to get a 0 there. Right away we will start that way. We are operating R2 by R2 minus R1, and we are operating R3 by R3 minus R1, and we are checking what is happening. This is minus 1, this is minus 1, this is minus x, this is minus y, minus x, minus y. Right away we will see what is happening. 1xy, 0, y, 0. And 1 we have always this convenience. So this is 0, 0, x. And this is fair enough. We don't have to do anything much. Why? Because the n number of zeros is there, 1 is there. That's enough. We can expand. So let's expand. 1 time this, it will be xy. Then this entry, minus x times 0, y times 0, So leftover term is xy. That's all. That's the answer. No? Xy. It expands as xy. That one was a blessing for us. It came up like too good. So this is our next matrix. Alpha, beta, gamma, alpha squared, beta squared, gamma squared, beta plus gamma, alpha plus gamma, alpha plus beta. We've got to show that this is there. Now one thing that's very, very glaring to us is alpha plus b. If you could add this will be common in all the cases, right? So I'll just consider the LHS. This is our problem number 11. Yeah, it's very difficult to copy it again, so we'll just continue. We'll consider the LHS from there, and we are first doing C1 and C3 we will add. What is the advantage? It will become alpha plus beta plus gamma in all the cases, right? Alpha squared, beta squared, gamma squared. So I think we could have added it on C3. Oh, that was better. We could have added it on C3 becomes C3 plus C1. That's better rather than doing this. Why? Because these single ones are much easier to handle. Alpha, beta, gamma. So this will be alpha plus beta plus gamma, alpha plus beta plus gamma, alpha plus beta plus gamma. Have that removed. Alpha plus beta plus gamma. Remove. So what is coming here? Alpha, beta, gamma, alpha squared, beta squared, gamma squared, 1, 1, 1. That solves your problem quite a lot. So this is already there. Now you require beta minus gamma. That means you require this minus this. Then you require gamma minus alpha. That means you require that minus this. Or like that. You see it and you do it. So beta minus gamma. So you can have R2 becoming R2 minus R3 and check what comes. So alpha plus beta plus gamma out, and you're doing R2 minus R3. Alpha squared 1, beta minus gamma, beta squared minus gamma squared, and 0. Right, and gamma squared 1. So we can see that beta minus gamma is common throughout in the row 2, so that we can take out. Beta minus gamma can be taken out. We are left with alpha squared 1. We are left with 1, beta plus gamma, and 0. We are left with gamma squared 1. So that's the thing. So we have got beta minus gamma out, and then next we require gamma minus alpha. So maybe we can have R3 minus R1. So let's check R3 minus R1. R3 becoming R3 minus R1. How will we get that? So we are going to get maybe alpha plus beta plus gamma into beta minus gamma, and let's check now what we can do here. It is alpha squared 1. Here it is 1. Beta plus gamma 0, gamma minus alpha, gamma squared minus alpha squared, and 0 here. So like before, this gamma minus alpha is common, beta minus gamma, and gamma minus alpha is common. So what are we left with? We are left with alpha squared 1, beta plus gamma 0, and gamma minus alpha is out. So 1 is there, gamma plus alpha is there, and 0. A squared minus b squared breaks as a minus b into a plus b. That is what we are doing here. Right. So that's about that. If you want, as a measure of convenience, you can get a 0 here. Then we can go in for an expansion. So maybe you can do maybe R2 becoming R2 minus R3 or R3 minus R2. What will happen? Let's check which is better. We are going to get beta minus alpha. Do we require that? No, we require alpha minus beta. So we will do R3 minus R2. Right, this will come by observation. Alpha plus beta plus gamma, beta minus gamma, gamma minus alpha, and we are doing this. So alpha squared 1, beta plus gamma 0. This is 0. And this is minus beta minus gamma goes, and then you are having alpha minus beta 0. Now therefore this can come out. So we are left with alpha plus beta plus gamma times beta minus gamma, gamma minus alpha, and alpha minus beta as common one has come out. So our determinant is having alpha squared 1, beta plus gamma 0, and 0 1 0. So we can think of expanding. So let's see what will happen in the expansion. All these terms are as it is, alpha plus gamma, beta minus gamma, gamma minus alpha, alpha minus beta. Then alpha times will not come because these both are 0. I think alpha squared also will not come, only this term will be remaining, and that will be 1 on expansion. We can actually sit and see. We get only the last term will be there on expansion, and that also only 1 is there. There is no other factor there. Finally, that is our RHS, and that's how we prove the result. So that's about it. There are more problems in the miscellaneous. I think, yeah, that will take up in the next video. Thank you.